Hello everyone, nice to meet you all. My name is Chengzhi. I am from Kaiser Institute for Technology. Today I would like to give a talk regarding my paper, MotorFactory, a blend add-on for large dataset generation of small electric motors. Here is the content of my presentation today. The MotorFactory add-on is initially designed and made for the learning purposes in our ArchiProbot project. Firstly, we would like to give some introduction about the project itself and why the add-on helps our research. Then, related work on other synthetic datasets will be reviewed. After that, we will give a detailed introduction to our MotorFactory add-on and show how can we use it to create a synthetic image dataset, as well as synthetic point cloud dataset. Then the application use cases for the add-on in our project will also be discussed on various manufacturing or machine learning tasks, including intralogistics tasks, inspection tasks, and disassembly tasks. Finally, a conclusion will be given. Now let's start with the background introduction, which is the ArchiProbot project. To enable automatic disassembly of different product types with uncertain condition and degree of wear in remanufacturing, agile production systems that can adapt dynamically to changing requirements are needed. The ArchiProbot project aims for auto-detection, tracking, and disassembly of end-of-life products. To be specific, in our current experimental setting, we work on small electric motors used in vehicle manufacturing. Universal methods need to be developed to deal with various types of motors, including the ones with unseen specifications. This is a 5-year-long project, and it involves 9 chairs at KIT. The 9 chairs are responsible for different tasks in different fields respectively, including manufacturing, logistics, robotics, and computer vision. Also, they need to cooperate with each other to make the whole pipeline work. In our case, we divided the pipeline into 4 stations. In most stations, machine learning algorithms are employed due to their generalization capabilities of learning from various types and variants of products. However, in reality, datasets with a diversity of samples that can be used for training the models are difficult to obtain in the initial period. This may cause bad performances when the system tries to adapt to new unseen input data in the future. In our case, at the early stage, we are only provided with a handful of motors with only few different product specifications. The variance of data is actually not sufficient for training with machine learning methods, especially those deep learning-based ones. To deal with this problem, we created a blend add-on named MotorFactory, which can generate motor mesh models with a variety of specifications based on the motor types we have currently. Furthermore, it can be used to create large synthetic image and point cloud datasets, which may be used for various tasks in our project. Speaking of synthetic datasets, there are also lots of other interesting related works. Regarding synthetic dataset of 3D models, ModelNet provides a collection of around 100,000 models for 3D object classification and retrieval. More than 3 million annotated 3D models are collected in ShapeNet. Its subsequent work, PartNet, additionally offers fine-grained semantic segmentations information for a subset of the models. By utilizing Thingiverse, Thingy10K provides a large dataset of 3D printing models. More recently, the ABC dataset collects over 1 million CAT models. Regarding 3D themes, Sincere and Proxy consider urban themes, and each provides a dataset for semantic segmentation in these environments. There are also other approaches in the image domain deal with the generation of images from specific themes. On the other hand, SimCity gives an example of generating point cloud synthetic dataset, which in contrast to the previously mentioned works, point clouds of urban themes are generated using Blender. Our MotorFactory add-on is also designed and made with Blender. As an open source software, Blender is a proven tool that performs well in modeling shapes and creating highly customizable add-ons. Our MotorFactory add-on is able to generate mesh models with various specifications and save them in desired file formats. Considering different requirements, the add-on is implemented in two versions. Version 1.0 only considers the components of motors that can be directly observed from the appearance, while version 2.0 further considers the inner components. The generated models of both versions contain the following components: pull port, electrical connection, gear container, cover, and bolts. Regarding inner components in version 2.0, the additionally generated parts are magnets, armature, lower gear, and upper gear. This is an explosion figure of a motor generated with version 2.0. The original assembled motor model is also shown at the rightmost. To generate motors with various specifications, we provide lots of parameter options that control the type, size, position, and rotation of different parts of a motor. For example, bolt positions, gear size, or per port length. Additionally, both versions provide multiple bolt generation options to meet different requirements. With the help of the proposed MotorFactory add-on, we present a large synthetic motor dataset for our ArchiProbot project. With it, one can create motors with lots of variants easily. Hyperparameters like the length of the metal part, the position and the diameter of the gears, the position and the bit type of the bolts, etc. have been predefined. Surface materials have also been attached in case of necessary rendering. The default rendering scene consists of a motor, a climbing system, a background panel, a camera, and some lights. Now, we can easily render a RGB image in Blender. Besides, with the help of other tools, we can also generate a corresponding depth image, a normal image, and a segmentation ground truth image. For each time, we use a random motor model and a random camera setting for the rendering. Here are some rendered results with different settings. Additionally, random background images may also be attached to models. Note that we keep the shadows to make it more realistic. The corresponding depth images, normal images, and segmentation ground truth images are also available. Apart from the synthetic image dataset, we can generate synthetic point cloud dataset accordingly. Once the models have been created, artificial point cloud data may be acquired with another sensor simulator add-on, Lanza. Here is a demo comparison between the point cloud generated from Lanza and the point cloud obtained from the Zwift camera. After downsampling both point clouds to a same number of points, we can observe that they are quite similar to each other. The synthetic point cloud dataset is suitable for pre-training in this case. With the help of Lanza, we can also generate a corresponding point cloud for a certain scene used for rendering 2D images. The point cloud also includes color information and semantic labels. We generate point clouds for all the scenes as shown here. The motor is generated with random parameters from our MotorFactory add-on. The position and the perspective of the camera also vary in a certain range. All those parameters are saved in CSV files. The ability to generate synthetic motor dataset enables the development or improvement of a variety of different use cases inside the interdisciplinary ArchiProbot project. The presented use cases follow an exemplar product flow inside the ArchiProbot demo factory as illustrated here. The intralogistics system is responsible for transfer the product to a station and handle it with a vision-based manipulator, depending on the station type. Inspection-related tasks all disassembly procedures are carried out. The object transfer control workflow includes a vision system mounted on the autonomous mobile robot, which is used to detect and track objects on the transfer units. Detecting objects and estimating their pose is essential to realize the decentralized control between the autonomous mobile robot and the transfer unit. In our case, by feeding generated motor models to Blender to generate static image data, one can create high-quality re-rendered images with accurate ground truth annotations. Enriched with labeled real-world images, one can create a dataset of reasonable size to train well-performing real-time detection and tracking network models. Regarding the object handling task, the grasp detection system is the key entry point and includes the target object localization, the object pose estimation, and the grasp estimation. To solve the localization and the pose estimation problems for known objects, simple bounding boxes, as described in the previous use case, are not sophisticated enough. However, since the MotorFactory generates mesh models on part level, annotated instance segmentation masks can be generated. Training a segmentation network like mask RCN allows to detect pixel-level segmentation instance of classes. For object inspection tasks, the formalized problem of completing product surveys converge using a robot-based optical system can be expressed as a view planning problem. To solve this problem, model-based approaches determine robot poses for sensor sensing by pre-planning based on a prior model, while non-model-based approaches determine the next best robot pose for acquisition at runtime through maximizing certain criteria. However, in many cases, independent remanufacturers do not have product information, such as mesh models of the product at hand, due to confidential issues. This hinders efficient pre-planning of visual strategies for inspection. With the help of the proposed MotorFactory add-on, an important research gap can be approached. For disassembly tasks, in our case, the target object is set fixed in a fixture when it is transferred to the disassembly station. Then a real-world point cloud is obtained with the vivid 3D camera. However, the variance of different taken point clouds, especially regarding the motors, is not sufficient for learning purposes. In this case, I create a synthetic point cloud dataset using the proposed add-on. After the network is pre-trained with the synthetic dataset, transfer learning may be applied with a few real-world data to fine-tune the model. Further important specification information, such as bolt positions, may also be obtained with additional post-processing algorithms and subsequently provided to robots for further tasks. Some qualitative demo results on the point cloud segmentation task are also given here. From the figure, we can observe that after pre-training on the augmented synthetic dataset and fine-tuning on the real-world dataset, the network can perform well on the point cloud segmentation to provide bolt position information. Okay, now let's move to the last conclusion part. So in this work, we present MotorFactory, a Blender add-on which allows the end user to automatically create a variety of different small electric motor models and components. Based on the generated models, synthetic datasets can be created for different computer vision tasks. Being able to generate and annotate product models easily may further increase the level of automation in challenging remanufacturing environments. Inside the interdisciplinary ArchiProbot project, we identified several use cases for the intralogistics, inspection, and disassembly domains. All of the use cases benefit greatly from having access to synthetic product models. In the future, an open-source benchmark dataset for object attribute estimation based on the add-on will be created and published. New versions of the presented add-on may also be developed. Okay, that's all for my presentation today. Thanks for listening.